Hey, welcome to my channel Physics Tutorials with BK, where you will learn with fun. So, welcome back to my channel, and we will proceed. But before proceeding, I will request you, if you like my videos, then like and share it. And I am very sorry for not uploading and recording the videos for the past 5 days, because my camera was not working properly, and that's the reason. But leave it. We will proceed with our topic, which is the nature of physical laws. There are three laws of motion discovered by the Newton. We shall study this and discover how these motion laws helps us in our classical mechanics, and how we able to conceptualize the things. Okay, so let's start. And here is our board. So we shall proceed with the nature of physical laws. So in a physical phenomena, as we all know, some things are constant while other are variable. In a physical phenomena, some things are constant while the other things are variable. So these three laws of motion formulated by, who formulated the physical laws of motion? The fundamental laws of motion were formulated by Newton. So Newton discovered these laws, actually were able to demonstrate and help us to understand whatever motion of objects is there. So if any objects in our daily life moves and change its position with respect to time, then it is governed by the three laws of motion. Not only limited to our daily life, but it is also applicable to the celestial bodies like stars and planets, etc. So we shall find out how these laws of motion are useful, and what are the three conservative laws. Okay, so first conservative law is the conservation of linear momentum. So what do you mean by conservation of linear momentum? It says that in the absence of any outside force, for example, in a system, if the force is zero, if the net force in the system is zero, and there are some bodies, let's say there are two particles inside the system, and they have some linear momentum due to their mutual interaction. The first one item is 1 and the second is 2, and the linear momentum respectively is P1 and P2. Okay, it's a vector quantity, so I am displacing an arrow up above it. Okay, so these are represented by P1 and P2, and the law of conservation of linear momentum says that there is a sum of linear momentum of the two particles remains constant. Okay, for say, if initially the linear momentum sum was 0, then after an interval of time the linear momentum sum will also be 0. So it does not change with time. Okay, it don't change with time, it remains the same, and you shall understand that this is the law of conservation of linear momentum. Okay, so next proceed with next, the law of, all our laws, law of conservation of angular momentum. Conservation of angular momentum. Now what is angular momentum? See, this pen is rotating. Okay, for say this pen is rotating, so in this rotation there is a thing like angular velocity omega. So this is nothing but angular velocity. if you don't know what is angular velocity, then you should first know what is the linear velocity. This is the linear velocity, okay, and this is a vector, so we can display an arrow here. So this is the linear velocity, and what is this? This is the angular velocity, okay. So what does the law of conservation of angular momentum say? It says that in a system, okay, here is also system. In this regard, we shall also take a system in which there are one particle or a system of particles, okay, and it's rotating about an axis. For say, this is the axis, and here is the particle. So it rotates around this axis, okay. In that rotation or that process, the angular momentum of this particle which is rotating around this axis remains the same. So it can be said that I omega is constant. Now here I is the moment of inertia. I is the moment of inertia, and omega is the angular velocity, okay. So as we all know, when I will give an example how this law of conservation of angular momentum governs. For example, there is a belly dancer, and this belly dancer is dancing. In doing so, this belly dancer, what does she actually does? She takes her legs and arms and folds it in the way that the distance from the axis, its main axis, to the extreme end, that is the extreme end of his legs and arms, gets reduced, okay. So in reducing the distance from the main axis to the towards the extreme points, when it do so like this, okay, so in doing so the moment of inertia gets reduced. And how does it happen? It's happened like this. The distance, okay, it's mk square, okay. So k is the distance from the axis towards the extreme point, okay. Here is the extreme point here, okay, but here the extreme point is here. So we can say that the k is reduced. Here k is this much, and here is k is this much. This is k, the distance from the axis to the extreme point of body. So this is k, okay. So this k gets reduced in the scenario when the ballet dancer is moving and folding her legs and arms. So when this get reduced, then moment of inertia also get reduced, and when moment of inertia get reduced, the angular velocity increase. How? Because if this decrease, then this will absolutely increase. So in this way we can say that this ballet dancer moves are governed by law of conservation of angular momentum, because we know that when she folds her arms and legs, the angular velocity, the turns per second, is increased. So how this turns per second increased? By the decrease in moment of inertia, okay. So I hope that you understand the conservation of angular momentum, but if you don't understand, when we do in this detail angular momentum in the next chapters, then you will surely have a good understanding of this law, okay. So without wasting any time, we shall proceed to our next law. Okay. So in the next law of conservation is the law of conservation of energy. Third is the law of conservation of energy. Okay. So see, all the laws of conservation governs every moving particle or object in our actual life or in the space. So how is able to do this? Because these three laws are the basis of the classical mechanics, and we can also prove this. Okay, so laws of conservation of energy. So it says that energy is neither created nor destroyed. Energy is neither created nor destroyed. Okay, so there is a contradiction toward this statement when we study the Einstein's mass energy equivalence relationship. Okay, in which we see that the energy and mass are interconvertible. See, if the mass is moving with equivalence to the light of speed, then it is converted this mass into energy. So we will shall study it later, but for now we say that energy is neither created nor destroyed. Okay, so see, now I will also explain you that what is the homogeneity of flow of time. Homogeneity of flow of time. It is a general principle. It is the general principle. Now, homogeneity of flow of time, what does it explains? It actually says that the time flows in a homogeneous manner. Okay, and this general principle can actually follows and move towards the law of conservation of energy. Then you probably question me and ask me, how can you prove it? Prove it, please. So if say that I will take an example of pendulum. Okay, the pendulum is hanging and not moving. Okay, it is the state of rest. But when the same pendulum moves in this, okay, in the to and fro motion, to and fro motion means one time it's on the left, on the other second it is on the right. Okay, so in this phenomena of the pendulum, when it is moving to and fro, then we say that as according to the homogeneity of flow of time, the time moves homogeneously. Okay, and this homogeneous flow of time, the energy is conserved. Okay, so in this state we say that kinetic energy is maximum and potential energy is minimum. And why so? Why kinetic energy is maximum and potential energy is minimum at this stage? Because here the potential energy is 0, or according to it, if we take the center here, reference here, then we can say the potential energy is 0. But otherwise, if we say if the reference is here, so there is some potential energy. Okay, please note that the potential energy always works with some relation, some reference. Every time there is a reference upon which we can say that this is the value of potential energy. Okay, please write it down, and let's take the potential energy as minimum here, because when it moves from right, okay, moves toward the right, then it raises the height of this central point, and when the central point raises its height, some potential energy is gained. Okay, because the reference is from down to up. Okay, when the height is increased, its potential energy increases. Okay, so here we can say its potential energy is maximum. Here is minimum, and here the potential energy is maximum, and the kinetic energy is minimum. Okay, so if there is velocity here, if there is some velocity, it gets reduced to 0 when it is here. Okay, at the point B, the kinetic energy becomes 0 because its velocity gets 0. But at the stage of this, the kinetic energy is maximum. Okay, kinetic energy is maximum. So similarly, we can also say that on the extreme left of this pendulum, when the pendulum is at extreme end, the kinetic energy is minimum and potential energy is maximum. So it raises some height, okay, its height gets increased, so potential energy increased, and because it is the last extreme stage, so this is the maximum height. So maximum height, maximum potential energy, and maximum velocity, so maximum kinetic energy. This is a simple law, okay. Please write it down, okay. If there is a maximum height, then maximum potential energy, and if this is maximum velocity case, then there is maximum kinetic energy. So I have taken this example to illustrate how the kinetic energy and potential energy are convertible into one another, but the mechanical energy is conserved. But the mechanical energy, which is the sum of kinetic energy plus potential energy, it is always conserved in all the stages of the pendulum in to and fro motion, okay. Wherever it is, the potential energy is conserved, okay. Potential energy and kinetic energy sum is conserved, which is called the mechanical energy. So write it down, and we shall proceed to the next part of our today's lecture, okay. So are you able to understand? Is there any questions? Please write down in the comment section, and I will surely give answers to all your questions. And please make sure, if you have any doubt, then please ask me, because my first priority is helping you understand all the basic concepts and fundamentals, okay. So due to that priority, please help me in achieving that goal, and I will be very satisfied if you are able to understand, okay. And if you want that my videos should be in Hindi, then please write it down, because I can also narrate in Hindi, but my major priority is that everyone, it is this video that should be given to everyone, okay. So Hindi is limited, but according to my sense, English is more means English is very spread in the world. So in any world part, if someone is watching, then it is the maximum chances of probability that he knows English. So that's why I am giving my lectures in English. So don't take it personally, okay. Now what shall we do? So I have already narrated you the 3 laws, so I will give you a quick recap, okay. So here is a quick recap. The law of conservation of linear momentum, the law of conservation of angular momentum, and the law of conservation of energy, okay. But I have not told you the very famous relativistic principle, relativity theory of Einstein. So according to the relativity theory of Einstein, there is a mass energy equivalence. We can also say that this relativity theorem of Einstein can also be said to be mass energy equivalence, relation, okay. So how this statement goes? This statement says that E is equals to mc square, okay, means energy and mass are interconvertible, okay. So it says that if we take E by c square, by taking c square this side, then this is equivalent to mass, okay. So what he says that this particular mass is equivalent to some energy. This particular mass is equivalent to energy, or we can say that now we can say that if you take the mass, if you take the energy, so energy is equal to mc square. Okay, so this particular energy, we know that this is energy. Einstein said this particular energy is equivalent to some mass. Okay, this particular mass is equivalent to energy, and this particular energy is equivalent to mass. Okay, so now what is c? C is the speed of light. What is the c? C is a constant, that is speed of light. Now we all know what is the speed of light. It is 3 into 10 to 8 meter per second. Okay, we can also write it down as 3 into 10 raised to power 8 meter per second. Okay, so I hope that you understand the mass energy equivalence relation of Einstein and how it goes. It says that E and M, the energy and mass, are interconvertible. Say if a mass achieves equivalent to the speed of light, okay, so its sum of its mass get converted into energy, and vice versa. If the mass gets destroyed, it is converted into energy. For example, we can take the example of a nuclear fission. In the case of nuclear fission, what we see that in case of nuclear fission, some mass is destroyed. This is the mass, okay, and when this unstable mass, we say it unstable because it has high mass. Okay, it has high mass. That's why this particular element is unstable. You can take as uranium also. So once it gets converted into two smaller masses with the help of nuclear fission, once this gets converted into two smaller masses by any mechanism, let's say we hit it with a very strong speed moving particle. So when the strong particle hits it because of its unstableness, it gets converted into two smaller masses. So these smaller masses, when converted, it gets ejected with a high energy, So as we say that the high energy can be equivalent to the mass. Okay, so this high energy, if you convert this high energy into some mass, let's say this is the mz, so that m1, then m2, and then mz, this is the total mass on the right side, because the high energy, if we get equivalent to mz, okay, so this sum of m1, m2 and mz is equivalent to the unstable mass of the uranium here. Okay, so this is the mechanism which says that how the mass is conserved and the energy is conserved, but these mass and energy are interconvertible. So this is the mass energy equivalence relationship. Okay, so I hope that you have understand it, you are able to get what I am speaking. If you have any doubt, then please write it down. And I am watching that you are not liking my videos, so please like my videos and share with your friends, so that it reaches to large masses, and many of the students who are not able to get the concepts are able to capture these. Okay, I hope that you have all noted down it. Okay, so what's the basic purpose here? To let you understand the laws of nature and how it governs all mechanical movement, all mechanical motion in our daily life, as well as in the interstellar space or the celestial space. There is some mechanism governing this motion. So these basic conservation laws helps us to understand these processes or mechanisms. Okay, so today we will start right now with the system of units. System of units, it's the next chapter, system of units. Okay, board is not clear, but I hope you will get understand. Now the system of units. So as we all know, to measure anything, we need units. But for every particular physical quantity, there are some standard units which are to be used to measure that particular value. For say, if there is a length of any object and we have to measure the length of the table, for say, the length of table can be measured in various quantities, in various units. We can measure it in the foot, meter, centimeter, millimeter. We cannot say kilometer because the length of table is not too large that we can say kilometer. We can say decimeter. Okay, so range of different units, but there are some standard units for every particular physical quantity. Okay, there are some absolute quantities which Newtons have taken, that is the length, mass and time. Okay, I would say these are three basic and most absolute units which have been taken by the Newton to explain the three laws of conservation. Okay, so what I am saying that for measuring any quantity we have to take the help of units. Now yes, so we can elaborate any physical quantities, let's say it x, into a formula nu. Okay, where n is the, this is the x is the physical quantity of an object. It can be length, it can be mass, it can be time, okay, anything. So this is the physical quantity. N is the numerical value. And what is u? U is the unit system. Okay, we can take any unit. Okay, let's say we can take millimeter, centimeter, decimeter, meter. Okay, any unit we can take. So it is the product of numerical value and unit. For example, if we say that the 3 meter length of a table, the length of table is 3 meter. So here 3 is the numerical value and meter is the unit of that length. Okay, we take the length of that table as 3. Okay, 3 is the numerical value, but what unit we have chosen? We chosen the unit as meter. Okay, now this is the basic example. So what if we have to convert this 3 meter into centimeter? So we shall again use this basic formula, that is x is equals to nu. This is constant. The physical quantity of an object cannot be changed. Okay, so if this whiteboard marker have the length this much, so this much length, this much physical quantity will not change with the respect to time. Time can't change this length. Okay, so if I have to change the unit, absolutely the numerical value gets changed, but the physical quantity remains unchanged. So if I convert this 3 meter into centimeter, what I have to do is, I know 1 meter is equals to 100 centimeter, and once I will put this numerical value as 3, and in place of 1 meter I will put 100 centimeter, and it gets converted to 300 centimeter. See, this is the N1 U1 and this is the N2 U2. N2 is 300 and U2 is centimeter. Okay, the product of the same physical quantities in various units remains unchanged. Okay, so this 3 meter is equivalent to 300 centimeters. So this is the basic example of how we measure the things and how the physical quantity of any object is convertible into another units. Okay. Okay, wait a minute. Okay, let's proceed to the next. So I am saying that we shall give you to the system of units. Now what is system of units? There are some system of units, like first one is, we can say that CGS system. Now what is this CGS system? When we elaborate this CGS, this refers to the C for centimeter, G for gram, or G as in gram, S as in second. Okay, so centimeter, gram and second, these units are used as the basic units in the CGS system of units. So this particular CGS system of units was used in France, and has come from France. Now what we say that the CGS system of units is based on the centimeter, gram and second, as we have already understand. So this is the basic system of units which was discovered from France. The second is the FPS system of units. FPS system of units. Okay. Now F is foot, P is pound, and S is second. As we all know, foot is the unit of length. Here also centimeter of length. P pound is of pound. This is for the mass. And second, now second is for time. Okay, length, mass and time. So we are using these fundamentals, and for this fundamental units we are taking this foot, pound and second. So this comes from the Britain, Great Britain. Okay, but this FPS system is not used right now, and it's more conventional, and we can say that not used currently. Okay, so what I am saying that FPS system of units is not metric system. It is not the metric system, but this is a metric based system. Okay, CGS is a metric based system. Now let's proceed to the next. I think, are you able to understand all this? And the next is the MKS system of units. Now what is MKS system of units? Now MKS system of units is M as in meter, okay, K as in kilogram, the measurement unit for the mass, then S as in second, a unit for measuring the time, same, second for time, kilogram for mass and meter for length. Okay, now where this MK system, this was set up in France. So we have seen that two system of units have been set up or discovered in France. One is the MKS system of units and the other is CGS, and the one is from Britain, which is FPS system of units. Now this particular MKS system of units is also metric. This is the metric system of units. We can say also metric system. Okay, so but this is FPS is not metric. Okay, so these are some system of units, common system of units. We can say that these are common system of units which we generally use in the measurement of different objects. Okay, or we can say length, mass and time. So measuring the length, mass and time, the common system of units are, one is CGS system, the second is FPS system, and the other is MKS system. So CGS and MKS are the metric based system of units, but the FPS is non-metric based system of unit. Okay, so shall we proceed to the next part of our video tutorial? So let's begin to the next part. Okay, so right now I am writing down some basic physical quantities like length, mass, time, temperature, pressure. This is some other basic physical quantities, and in the second column I will use the units for measuring these basic physical quantities, and in the next table I will use some abbreviation. Okay, so there are some 7 basic physical quantities: 1, 2, 3, 4, 5 and 6 and 7. So what are these? These are length, mass, time, temperature, light. Okay, and then the this light is actually, we can say, luminous intensity also. Okay, luminous intensity. Now electricity, and the next is the quantity of matter. Quantity of matter. So these are some basic physical quantities. These are some basic physical quantities which we generally use to measure different scenarios. So for example, if you have to measure the length, okay, what will you use? We can take meter. Meter is the standard unit. Okay, so in this column I am using the standard units. Okay, standard unit for measuring these basic physical quantities. Now as we all know, the basic physical quantity for length is meter, the mass is kg, the time is second, temperature is Kelvin, for light or luminous intensity it's candela. Okay, it's only single L, candela. And then electricity we use ampere. Okay, then quantity of matter, mole. So these are the standard units for these basic physical quantities. Okay, these are the 7 basic physical quantities. When we use the dimensions, we use these basic physical quantities to derive any dimensions. Okay, for example, if we have to derive the pressure, okay, this is the next part of our tutorial, but I am giving an example of this dimension. So the dimension of, what is the dimension of pressure? So dimension of pressure can be derived by its formula. Formula is force per unit area. Okay, so force, as we all know, is mass into acceleration. Mass into acceleration. Okay, when we multiply the mass into acceleration, it gets force. So we can say this kg meter per second square, area meter square. Is it okay? Okay, so mass into area. Mass is used in the kg, and here acceleration meter per second square. So we have to take in the dimension formula. So here is dimension L, mass for what we use for the mass, capital M. Okay, capital M. And for time, what you will use time for time? It's T. Okay, temperature, Kelvin. Okay, then luminous intensity. What we use for the luminous intensity, the basic thing is that we use candela, C, electricity, ampere, A. Okay, these are the dimension used in the dimension formula. Quantity of matter, mole. Okay, so here what we use is, I think, a small mo. Okay, please check it whether it is right or not. It's mo. So this is our next part of our chapter. MLTA, I should say, right, and then we have quantity of matter. Okay, that's all right. So let's proceed to the dimension of pressure. There is a force per unit area. Now these are the some basic quantities. These are units. Okay, kg is a unit, but we have to convert into the dimension. So kg dimension will be m. Meter, we can use L. Second, we use T minus 2, and again meter square L2. So the dimension of pressure will be M1 L1 minus 2. So L minus 1, 1 minus 2 minus 1, and T minus 2. So this will be the dimension formula of pressure. Okay, this is the dimension formula for the pressure. Now let's take another example. Okay, so we should use the resistivity. We shall use the resistivity. Resistivity. Okay. So we should know the formula of resistance first. That is R A by L, which is the formula of resistivity. Now resistance formula is M L square T minus 3 A minus 2. Okay, into area L square divided by length. So this comes out to be M L 4 minus 1 3 T minus 3 A minus 2. So this comes out to be the formula of resistivity. So in this way we derive the dimension of resistivity. So let's proceed to the next. Your symbol. What is the symbolic formula of abbreviation used? Okay, abbreviation used for this. So its length. So meter is used. Actually here we will say meter. Okay, so the symbol will be M. Here is the kilogram, symbol is kg. Here is the time second, symbol is S. Kelvin, symbol is K. Candela, symbol is CD. Ampere, symbol is A, and mole, symbol is MOL. Mole, symbol is MOL. Okay. So these are the symbols we use for these basic physical quantities. Now there are some supplementary physical quantities. There are some supplementary physical quantities. Now I should help you know that all these are based on some reference book which I am using right now, and there are some extra topics in addition from the NCERT syllabus. So if you don't want to see these videos, you can just take your video to the next part of the lesson, so that you're not wasting your time. Okay, it saves your time also. So this covered because some students want some extra knowledge and information for their competition exams, and my purpose is that I will cover all this to help those students also which are hoping to give the exams of competition. Okay, so some supplementary physical quantities also are there. There is the angle. Is there linear angle? Then solid angle. These are the two supplementary physical quantities, and their units are radian and steradian. These are the units. Then there is some abbreviation. Radian is used as RAD and steradian is SR. Okay, this is their abbreviation. So you should write it down so that we can proceed with the next topic of our tutorial. So write it down. Okay, so let's proceed to our next topic. So I have enumerated some units which are used to measure smaller quantities as well as some larger distance quantities. So the smaller length units, these are some smaller length units. Okay, so if the length of some unit or some object or some particle is very small, okay, that we cannot use the units like meter, centimeter, millimeter. So these are some units like 1 Fermi, which is equal to 10 to the minus 15 meter, then 1 micron, which is equal to 10 to the minus 6 meter, 1 nano, which is equal to 10 to the minus 9 meter, 1 angstrom, which is equal to 10 to the minus 10 meter. Then there's units we use to measure very large distance like astronomical unit. So this 1 astronomical unit is equal to 1.496 into 10 to the 11 meter. Okay, then 1 light year equals to 9.46 into 10 to the 15 meter. 1 parallactic second, it appears to be the unit of time, but it actually is the unit of length per second. It is equal to 3.0 into 10 to the 16 meter. Please write it down all so that you can remember all these quantities and units. Okay, so for now our tutorial will end here, but I am giving you a homework that whatever I have enumerated and explained you in the today's tutorials, you should please revise it, and this will be very helpful in our next videos and tutorials so that you have a better understanding of all the basic concepts. Thank you and have a nice day, and enjoy your time with the laws of physics. Okay, thank you.